Welcome to note set 17b. We're going to start talking about the four subspaces. So once you get this idea down, it really is kind of the big picture machinery of how all the important things in linear algebra work. And you can carry this forward to understanding lots and lots of things that are crucial in electrical and computer engineering. Junior level classes that we teach, senior level, even grad level classes, these things lie at the foundational underpinnings of so many electrical and computer engineering things. Not everything, but a significant portion of stuff in electrical and computer engineering can get traced back to understanding these four subspaces. So in this set of notes, we'll be talking just about the dimensions of them. How big is each subspace? Now we've seen almost all of these subspaces before. Yep, there it is. Hopefully we got that taken care of now for a while. So here we're talking about the row space, and we denote that as the column space of A transpose. And if you think carefully about what we're talking about here, this is for an M by N matrix, so transpose is N by M. So each column in A transpose is a vector in Rn. So this is going to span some subspace in Rn. There are cases where it could span all of Rn, but in general it's going to be some subspace of Rn. Then we've got the column space of A itself. And since this was a subspace of Rn, now we're looking at the transpose of that. Obviously this is going to be a subspace of Rm, because the columns of A itself are m-dimensional vectors. Then we've got the null space, which we denote as N of A. Now think about what that is. That's the set of vectors x that when we multiply into A gives us 0. So these vectors have to have n elements because A is an M by N matrix. So to just allow them to be multiplied, x has to be an element in Rn. But not all elements in Rn make Ax be equal to 0. So it will be some subspace of Rn. And here's the new one that we have. And you can see that it's kind of predictable what we should be looking at. We had the column space of both A and A transpose. We've got the null space of A, so we should have the null space of A transpose. And here we've called it the left null space. We'll see why in just a minute. But if we think about this now, we need to find x, or we might use y instead of x. We need to find, let's use y because I used that on subsequent slides. We need to find all the vectors y such that A transpose y equals 0. So since A transpose is N by M, Y must have M elements, and so it's going to be a subspace of Rm. So we now know where these subspaces live, what they're subspaces of, but we need to find out how big they are within the spaces where they are living. Let's just, before we go on, talk about why we call this the left null space. So if we think about taking our original matrix A and multiplying something in from the left, that gives us 0. So since it's coming in from the left, we call it the left null space. Okay, so how does that link to what we were just talking about? The null space of A transpose? Well, if we transpose both sides of this, so we would put parentheses around this and do a transpose on that. Do a transpose on this. Well, 0 transpose is just 0. Remember, when we apply transpose to a product, we have to interchange and then transpose each. So we would have A first, but with a transpose on it, followed by y transpose transpose, which would just be y. So this becomes the vectors y that are left null space vectors for A become right null space vectors for A transpose. So the left null space is the null space of A transpose. And as we've already said, that's a subspace of Rm. So it's interesting here to note that 2 of these 4 subspaces come directly from the A matrix, and the other 2 come from A transpose. Let me clear some of this ink off here. And the other thing to note is that the column, we have a column space from each, and we have a null space from each. So keep that in mind. That's how you can kind of think of what spaces we're talking about here. So let's look at the big picture of these 4 spaces, and I put this of A, M, N up here so that we can keep track of what the M and N come from. So M is the number of rows of A, N is the number of columns. So we can draw a rectangle here, and you know, I caution you that this is not an exact drawing of what these spaces are going to look like, right? These are going to be subspaces of some high dimensional subspace, and you know, it won't look like a rectangle, but we're going to draw it as a rectangle. So that's the column space, and what that is it's all vectors of this form. So pick any x, multiply it into A, you'll get a vector. That vector must lie in this column space. So that's what it means. That's how we defined the column space. Then over here we have the null space, which we'll define as all x such that AX is equal to 0. Then we've got the row space. Now, we won't get into why we're orienting these things the way that we're orienting. And again, remember, these are just evocative pictures. We're trying to evoke the idea, not show precisely the shapes of these spaces, because obviously they can't just be rectangles. And then we've got our left null space, which we'll put down there. And again, we'll see why these things are being oriented the way that they are oriented. And since we know that the column space and the left null space both are subspaces of Rm, we can kind of think of those 2 subspaces somehow making up Rm. And then the other 2 are subspaces of Rn. And I'm going to kind of get in trouble here graphically. Obviously Rn and Rm cannot be the same, so they will look like that. And again, I'm not saying that this is really the shape of Rn or Rm, obviously. We can't even draw those, but we can kind of draw evocative pictures of them. And what we will see, we haven't necessarily proved all this, but we actually have some of it. The dimension of the column space is R. That's actually by definition, right? That's how we defined the rank of a matrix. We said it's the number of linearly independent columns, the maximum number of linearly independent columns in A. And then that is by definition, since the column space is the span of your columns, the rank of the matrix ends up almost by definition being the rank of the column space. In fact, you could actually even have that as its definition of rank. And we also saw that the rank of a matrix is equal to the dimension of its row space. So we have the dimension of the column space of A transpose is also equal to R. That was a fundamental property of the rank of a matrix. And now we get into things that we haven't really addressed, that the dimension of the null space is n minus r. I think we've kind of addressed that to some degree, but maybe not completely. And the dimension of the left null space is m minus r. And I'll point out one interesting thing here. Notice that the dimension of the column space and the dimension of the null space add up to the dimension of the whole space, and that works over here too. So we've got R and we've got n minus R. You add those together and you get n. So on both sides that works, and that's a key insight to these spaces and how they interact together within the context of their underlying space, either Rm or Rn. So we'll talk more about that. And this is just stating what I just said, that these rectangles are not precise characterizations of the shapes of these spaces. They're just evocative of how the spaces should be thought of. So let's talk about the 4 subspaces for R. So what is R? Well, we've been talking about A, and it's not always obvious and easy to find what these 4 subspaces are for a given A. So we'll start our discussion with a row echelon form. So suppose we're given some A, and we come up with its reduced row echelon form R. Let's look at that. And it turns out that it's really easy to think about the 4 spaces for R. And here's some important points that will be made clearer as we go through this. So the dimensions of the 4 spaces of R are the same as for A. So all we really need to do is look at the dimensions for C of R transpose and N of R and show that there are and N minus R respectively. And then we look at, in Rm, we look at the dimensions of C of R and N of R transpose and see that they have these. And we'll be able to argue that those dimensions for the R matrix will be the same as the dimensions for the subspaces for the A matrix. But what we will see is that even though the dimensions are the same, the spaces themselves are in general different, at least for some of those, as we'll see. So our goal over the next several slides is to use this fact, kind of support this fact and use it to determine these results for the dimensions of these things. We already know the R results for the 2 column spaces. What we really want to see are the N minus R and M minus R part of this. But we also want to understand the second point, that even though we can easily find all of these spaces for R, it doesn't tell us directly what those spaces are for A. We'll have to do a little bit more work for that. So we'll illustrate this with an example while trying to make general statements, but also pointing out the results for this specific case. So here we've got some 3 by 5 matrix R, and we can see we've got 1, 2 pivot rows, and we've got a row of all zeros. Therefore, we know that our rank is equal to 2. So we know that right off the bat. That's easy to see. We also see that we've got pivot columns. Column 1 and 4 are our pivot columns. And so, as we've already discussed, the row space of R has a dimension that's equal to the rank of the matrix. And so for this example, we've seen that the rank is 2. And we can see that the row space, if we think about it as the column space of R transpose, these will be the 2 vectors that will span that subspace. In fact, there'll be a basis for that subspace. And since there's 2 of them in a 5-dimensional overall space, they'll form a 2-dimensional subspace in R5. And the basis for those are the 2 non-zero rows of R. So, Oh, I don't know why I got that out of order like that. Hopefully I don't have that on all of these. So the row space is a subspace of Rn, and those are the two columns. Okay, good. I don't have a problem with my animation on all the other ones, or I may have that on ones yet to come. I don't know, but so far it's looking good here. Let's continue here. We're looking at the column space of R. We know that's a subspace of Rm, so m is 3, so all the columns are 3-element vectors, so that makes sense that we're in R3. And again, by definition, the link between the column space and the rank is something we've talked about already. So the column space has dimension that's equal to the rank. And so in this case, we can easily see, because there are two pivot columns, we can see that the rank is equal to 2, and we can see that that those vectors form a basis for this two-dimensional subspace. So there's one of them, there's the other one. We've rewritten them down here, and clearly you can see that those are independent. So they span the column space. They are independent, therefore they are a basis as well. And we know that we only need 2 of them. If we go here and talk about the null space, which we denote as n of R, which we've already seen as a subspace of Rn. So in this case, n is equal to 5. So remember, we need to think about 5-element vectors that go here, whose elements are chosen such that the product ends up giving us the 0 vector, which would be a 3-element 0 vector. And our claim here is that the null space has dimension n minus r. So on the first two, for the dimensions of the column space, we got that almost for free because of our previous discussion. But here, if you remember how we talked about the null space, we said that for this example, because we have only 2 out of the 5, and remember 2 is our rank here, so R out of the n columns are going to be independent and a basis of the column space. The remaining n minus r gave us 3 free variables. That gives us the number of free variables. So we've already talked about how n minus r gives us the number of free variables. And we also talked about how it's those free variables that give rise to the null space matrix that holds a basis for the null space. And the way we got that, remember, was we had a column for every free variable, because remember, these are our free variable columns. Those had to have a 1 here, and then a 1 here, and a 1 here, so that we singularly pick out each of the null variable or free variables. And so that's why there will be 3 columns in this. And so we are essentially establishing that this result is valid. And so for this matrix, we find the red numbers here are the elements that would have been the F matrix extracted out of that. And what we need is the negative of the F matrix, and we stick it in where the pivot variables are. So we get the 3, 5, 7 negated there, and we get the 0, 0, 2 negated there. So we've established that the null space has dimension n minus r. And then it's not very difficult to do the same kind of argument for the null space of R transpose. So it's going to have dimension m minus r. So I could go through exactly the same argument here using different terminology, working with R transpose, working with extracting finding the pivot columns for R transpose and so on. But basically, it's a little easier to see because what we get for R transpose, remember, we'll have R itself, these columns are its rows, and so remember we said to find the rank we just kept going down until we hit all 0 rows below that. Well, that for now R transpose, we're just going to keep going over until we hit 0 columns, and the number of columns that we have there will give us the dimension of the null space, because that would allow us to set this to be anything we want. These two have to be 0 because these two things are linearly independent. So we make all the variables, the first R variables will be set equal to 0, and the last M minus R variables are what allow us to form the null space. So we can easily find out that that's how that works. And so basically what that boils down to is to find the basis for this, we find the last M minus R columns of an M by M identity matrix. So you can see how we did that here. So the last M minus R, in this case M minus R is 1, so we take the last column of that. So you can see that what that does is it sets the pivot variables to 0, and it sets the one free variable to 1, and so that becomes a basis for that. So that's pretty straightforward. All right, so we've got the 4 spaces nailed down for R, and we understand the dimensions, and we understand, we looked a little bit at how to actually find out what spans those spaces. So now we need to see why the subspace dimensions for A are the same as the subspace dimensions for R. I mean, so far we haven't established that, so we do need to establish that. So we'll take advantage of this result that says if there's our A matrix and we want to get it into R, there's going to be some matrix E that will consist of elimination matrices and maybe permutation matrices, reordering matrices, but those all combined into one matrix E applied to A gives us R. And we also know that E is going to be invertible so that we can get back A from R. I mean, obviously we have to be able to get A back from its reduced row echelon form. So let's take a look at, here's one A that would give rise to this R that we've been playing around with. And it's a particularly simple case. So we've basically the first 2 rows are the same in A and R, and we've just tacked on this row at the bottom. And so really just going from here to there just involves basically canceling. Now we're going to cancel with that, and then we're going to add those 2 together to cancel that. So those would be the row operations that would be used. But the important thing to note here is that if we look at the R, it's easy to identify where the pivot columns are. So our pivot columns are here and here because we've got a pivot here and we've got a pivot there. So those are our 2 pivot columns. And a key thing to remember is that the pivot columns for R form a basis for C of R. And if we take those same columns, so when we say pivot columns of A, we just mean find where the pivot columns are for R and then take those same columns over here. They will form a basis for the column space of A. Now if we look at this, let me clear the ink here. If we go up and look at this, we see that here's our basis for the column space of R, and you can see that that will be actually a two-dimensional plane that will have no components in the third element, right? So every element on that plane will be number 0. But over here we see these are the columns that span a two-dimensional space, a two-dimensional plane in R3, but it'll be a tilted plane. So the plane over here for the column space of R is a non-tilted plane, but the plane for the column space of A will be a tilted plane. And so clearly those are not the same. Same dimensions, but different spaces. But now we have a clue as to how to go about finding it. We find R not for the sake of finding its subspaces, but just to find the positions of the pivot columns. Once we have those, we extract the corresponding columns out of A, and those will be the basis vectors for the column space of A. So it becomes easy to find it. It takes a little bit of work, but it's not horrible. So A and R have row spaces of the same dimension, and they are the same space. So here we were just looking at column space. Now we're going to go talk about the row spaces. So the row spaces have the same dimension R, and they are exactly the same space. So this is pretty easy to see because how do we get R? Well, R is found from various combinations of A. So, well, I guess I'm saying it the other way around. Every row of A is a combination of rows of R, and every row of R is a combination of the rows of A. So those row spaces aren't being changed because we're not really tilting the space or anything. It's the same combinations that form them. So in other words, what we're seeing is that row elimination changes the rows themselves, but not the spaces that the rows span. So the row spaces stay the same. So the first R rows of R are the basis of our column space of A transpose. So again, it's easy. We use R as a tool to get to the understanding of the spaces of A. So how do we pick the basis rows from A? Well, we can just figure out from R which are the pivot rows, and then just take those rows from A. So that's one way to do it. But since they are the same space, I mean, we could use the rows from here. Now, in this case, the rows from R and the rows from A are identical, but it won't always be that way. But they will span the same space. Okay, A and R have column spaces of the same dimension R, but they are different spaces, and we just talked about that. So that's what we started off on the first slide of this subsection about. So what that's telling us is that row elimination changes the column space. Remember, row elimination does not change the row space, but it changes the column space, so that's key. So the pivot columns of R are a basis of C of R, but we don't necessarily know they are a basis for the column space of A, and we've already seen that. So here's A and here's R, and what we can do is use R just to determine which columns to pick. Pick those same columns. So we just said this just a few minutes ago. We're just reiterating it here. Pick those same columns, and they will span the correct space in A. And we can kind of get some insight into the fact that the same positions have to be the ones that are the linear independent ones, because we've already showed that that if x is a solution to ax equal to 0, then it's also a solution to rx equal to 0. So a solution to rx equal to 0 would have a 0 here and a 0 here, and then some non-zero elements there. And that same solution would put zeros here and here, and then non-zero elements here. And so that's what tells us that the linearly independent columns are in the same position in A as they are in R. And so we can easily figure out the R pivot columns of A if we find R first, find where the pivot columns are, extract the corresponding columns from A, and we have a basis for the column space of A. Nice. Number 3, A and R both have null spaces of the same dimension, and they are the same space. So we've already talked about how once we find the n matrix, we showed that finding the n matrix clearly, because of how we find n, if we multiply Rn, we will get 0. But we also argued that this spans the null space of A, and therefore A times n must also give us 0. So we've established that in previous note sets. And therefore we can see that not only does n form a basis for the null space of R, it forms a basis for the null space of A. So they're the same space and obviously then the same dimension. And then the last one, A and R, have left null spaces with the same dimension m minus r, but they are not the same space. And so this is again the fact that row elimination changes something about column spaces. So we've seen before that the dimension of column space of A transpose plus the dimension of its null space must add to m, and therefore we end up getting the m minus r just like we had before. But to think about this, we know that once we know what the dimension of this space is for R, it's pretty easy to say, well, what we need to do is extract m minus r columns of the identity matrix. And we talked about that earlier. So if we just denote that idea this way, so the tilde here with the m minus r down here tells us that we've taken the last m minus r columns of this. I think actually I just wrote this backwards. Rows and columns. Yeah, I think that should be switched, so I apologize for that. So now what we're going to do is, remember we had this result starting off. We said that there is some invertible E matrix that when we apply it to A gives us R. And now if we just take the transpose of both sides of this, transposing a product will interchange them with transpose. So we get this result. And now look what we're going to do. We're going to take this I tilde matrix and hopefully we've made it the correct m by m minus r. I'll try to fix that in the notes before we post them. So now I've got this r here, which is going to be n by m, which hits the m first dimension of that, so that's good. And since this is holds the basis of the null space of R, we know that that's going to be equal to 0. But since these two things are equal to each other, we put the I tilde here as well, so we're basically just multiplying from the right on both sides of this equation. And what that does, let me clear some of this stuff off here because it's getting a little bit crowded there. What that does is, if we think about that, forms a basis for the null space of A transpose, since those columns hitting A transpose give us 0. And so what we see is that the basis for the null space of A transpose would be the last M minus R columns of the transpose of the E matrix. So that's what we've established here. So to see that, for the example we've been looking at, if you work it out, you start with the A that we started with. Here's the A transpose. But if you start with the A that we started with and look at how do we get the R from that, this is the E matrix that gives this result. E times A is equal to R for our given A and the R that we've been using. So here's our E matrix. And so what do we need to do? We need to transpose it and take the last M minus R columns. Well, in this case, M minus R is equal to 1, so we need the last column. So we're going to transpose it so this thing actually becomes the column read from top to bottom that way. So we get -1, -1, and 1. And you can verify that when you multiply that into A from the right, it does indeed give us 0. So it'll give us 5 0 elements on the right-hand side. So we've now covered all 4 of the spaces, and we've established the dimensions are correct as we predicted. So when we started off, we just wrote down what these dimensions are, and now we've explored that. We've not done a formal proof of these things, but we have started to understand, we illustrated or we made at least a reasonable argument. And this is called part 1 of the fundamental theorem of linear algebra. So part 1 just establishes the dimensions of them. Part 2, which we'll get to a little bit later in another set of notes, will provide a little bit more detail, and we'll explain why we've kind of oriented this one and this one as they are shown here relative to each other, and likewise why we've oriented those two next to each other. So the fundamental theorem of linear algebra, part 1, says that the column space and row space both have dimension R, and the null spaces have dimensions n minus R and m minus R respectively. And so that's the end of this set of notes, and I'll see you in the next set of notes.